and he's going to speak on programmable Hamiltonian for one-way patterns.
Hello, this is a joint work with Fatemeh Seifan and Elham Kashefi, programmable Hamiltonian for one-way patterns. Actually, the first computational model in the history of quantum computation was not quantum Turing machine, but it was a continuous walk on a line. Richard Feynman in 1985 proposed a Hamiltonian, as you see here, and he considered a system consists of two registers, one word register and the other clock register that he named cursor. And the role of cursor is to tell the unitary evolutions, which unitary evolution to act on which word qubit. Here in the Hamiltonian, U subscript T is a unitary evolution to be applied to the qubit, and the creation and annihilation operators are just to push the clock one step forward. And the complex conjugate here is to enable this to be Hermitian and to be Hamiltonian for a system. Actually, the main idea behind all of the Hamiltonian-based evolutions is the same. For example, in the construction of Kitaev that he proposed to simulate quantum circuits in a continuous time, he proposed a Hamiltonian that consists of different terms, one for checking the correct propagation of circuits, and the other terms just to ensure that we have a unique ground state at the end, or in other words, to remove the degeneracy. But with having a desired Hamiltonian, it's not the end of the task all the time. In some cases, you can't prepare your state in the ground state of the system easily. So we have a computational model called Adiabatic quantum computation that I explain generally here. Adiabatic theorem states that if you pick a simple and easy to prepare initial Hamiltonian and prepare your your system in the ground state of this Hamiltonian, and you evolve adiabatically to your desired Hamiltonian that here we call H of final, or final Hamiltonian. Adiabatic theorem states that you'll remain in the ground state of the system all the time. So, using this method, if we have a desired Hamiltonian, we can prepare our system in the ground state. Whatever I talked until here are very natural physical computational models that are continuous time, but we have many other computational models, just like here the measurement-based quantum computation. In measurement-based quantum computation, we normally have a graph state or a cluster state, or recently you can do your computation based on AKLT or inventory states as a universal resource. And just like the idea behind the quantum teleportation, you perform single measurements and push the information to the output. And at the end of the day, you will have your desired output states. Just like here, the Pac-Mans in the real world are single measurement devices that when you measure the qubits, you cut them from the graph and reform the graph and push your information to the output here. There are many interesting questions about the linkage between adiabatic quantum computation and measurement-based quantum computation, since it has been proved that adiabatic quantum computation has an inherent resistance against decoherence. On the other hand, measurement-based computation is naturally more parallel, and each of these models has its own specifications from algorithm design point of view. So we are seeking the linkage between these two models, and in this part of the project that I'm talking about today, we construct a new assembly language for MQC to be able to adapt it to the Hamiltonian-based evolutions. And we need our Hamiltonian to be translational invariant local. I have to explain why translational invariant. The people who are drawn to the Hamiltonian evolutions always claim that this is a very simple computational model because there is no active computational element, and the only thing you have to do is to wait until the algorithm ends. But we have to keep in mind that preparing the system and the spin chain, is a very hard task, and we have to apply as many techniques to make this task easier. So we are interested in translational invariant Hamiltonians. In the language of computer science, it means that you have same rules at every point. And we need it to be local because the more local your Hamiltonian is, the most robust it is against decoherence. And as I talked a little about adiabatic algorithm, we need our Hamiltonian to be evolved adiabatically. And at the end, we need it to be programmable. Generally speaking, a programmable Hamiltonian is or a programmable architecture in general, is an architecture that consists of two regions. One program region and the other data region. And the program region controls the actions to be done on the data region, and it should be capable of manipulating without hardwiring. In fact, you can have a if you have a programmable Hamiltonian, it means that you can have a general purpose quantum computer that is capable of installing software. I said that we designed a new assembly language for our programmable computer, but I have to say what was the old assembly language for the measurement-based computation. Measurement-based computation has a command set, as I described here, an N operator to prepare our qubits in plus state, and single measurement operation with angle alpha that we label the measurement outcomes with 0 and 1. Entangling operator is nothing but a control Z operation, and local corrections that there are poly corrections, and the measurements and corrections mainly are dependent on the previous outcome. And what is the new assembly language here? As you know, measurements always excite the system, consume the qubits, so we cannot have a real measurement, at least in this architecture, in our Hamiltonian. So we combined measurement and its dependent correction here and defined a new controlled X operation. It's nothing too complicated, it's just a controlled X operation, but the control gate looks to the plus minus alpha instead of 0 and 1, just like ordinary control gates. And here is the assembly language set of our construction. We need an identity gate here to make the commands arrive at the appropriate points on time. I just talked about controlled X alpha. We need our entangling operator as the previous ones. And for the locality reason, we need a local swap gate. Because, for example, you may need to manipulate one qubit at the beginning of the register and one at the end. And the only applicable technique that I can imagine is to use a set of swap gates to bring the ending one to the first, and this is the reason we use swap gates. And I have to talk a little about these two strange symbols, the empty symbol and the pointer. Naturally, just like these figures that are stolen from one of the early programmable architectures, naturally, the first idea that comes to mind when you are thinking about a programmable quantum computer, you may think that it will need 3 registers, one for program register and the other clock register, and the last one the work register. But we are not much interested in these architectures today because of the locality of the Hamiltonian, and we want to reduce we want to make the Hamiltonian as local as possible. So there is a technique called geometric clock to merge the program and clock registers, and these two, empty symbol and pointer symbols are actually our clock commands that I'll explain in a few later slides how we'll use them. Here we have to construct our Hamiltonian. The Hamiltonian we have to construct a Hamiltonian such that the ground state of this Hamiltonian gives us the output of the desired measurement-based algorithm, and the state space is naturally the data register and the other register that we call here a program plus clock register. And I just said that we have to make it translational invariant. That we have to have the same rules at every point. But what should be these rules? Here are 2 rules for Hamiltonian. The rule number 1 states that when empty symbol comes just behind command, that our commands are parts of our assembly language, the Hamiltonian should swap these two symbols and do nothing on the underlying qubits. And if a pointer is just behind the command, it should swap the symbols and perform the evolution of A on the two underlying qubits. And here's just the basic Hamiltonian construction, just like the previous ones, that they have one term for moving forward and the complex conjugate term for moving backward. But what are these R terms? As I written here, it should perform our rules. The first term here is for the empty symbol rule, that if the Hamiltonian sees this configuration, it swaps and do nothing on the underlying qubits. And here, just for rule number 2, now that we have a Hamiltonian for our quantum computer, we have to know how to translate our measurement-based pattern that as an appropriate initial configuration for the quantum computer. Here, as you just see in my simple example, we have to divide our commands, our registers, to two parts. One, the left part and the right part. The left part of the program region belongs to the K program symbols at positions Mn, where K is the number of command sequences, the command sequences here, and M is the number of work qubits. And we fill between them with empty symbols, and we put our command sequences in the following, and our work qubits just beneath them. Here I'll bring a simple example. Maybe for you who are more familiar with measurement-based computation, this is a very simple pattern in measurement-based quantum computation that entangles qubits 1 and 2 and measures the first qubit in angle 0 and corrects the second one with Pauli X. Here we prepare our system in its initial configuration, and the only pattern that matches our rules is just here, as you see. So in the first step, our Hamiltonian will swap these two, and the I gates, identity gates, will do nothing on the work registers. And the next step, these two parts that our rule matches our rule. Here, the entangling operator comes to here and entangles qubits 1 and 2. It goes on and on until here our controlled X with angle 0 performs the final computation, and when the left half of the program register and the right half swapped completely, then your algorithm is ended and you can measure your qubits or do whatever you want to do with them. So we performed the computation on 2 qubits, and I just talked generally about adiabatic computations. Here we have to pick an initial Hamiltonian and a final Hamiltonian and put them in this interpolation. And in adiabatic computation, almost the most important criterion is to check that the eigenvalue gap, the gap between the first two eigenvalues are not decreasing exponentially. So here is the lower bound for our algorithm. So you have to check that the L2 norm of the difference between the final Hamiltonian and initial Hamiltonian over the square of minimum eigenvalue gaps, you have to wait more than this time. And here's our programmable Hamiltonians for our adiabatic computation. The initial Hamiltonian, we add energy penalty to any state except what we need for our first configuration or initial configuration. So here this term checks the correct positions of the pointer symbols, and this one checks for the empty symbols, and here for the commands and the work register, work qubits that are prepared in plus, and here for the rest of the commands. And the final Hamiltonian, that is our desired Hamiltonian, is simply the H of EMC that I described before. This part is completely H of EMC that here move forward and backward, just like our Hamiltonian. And together with some other terms to remove the degeneracy and obtain a unique ground state, just like here to check the correct input, here to correct output, and here to prefer the correct transition terms. And fortunately, a simple technique in the first paper of proving the equivalence between the circuit model and adiabatic computation model, they proved that the gap will increase inverse polynomial with the number of gates, or in our construction with the number of commands. And recently, in 2007, Gates et al. Improved this gap estimation, and there are very simple techniques to show how the gap is inverse polynomial in the number of commands. But we have to keep in mind that our Hamiltonian for adiabatic computation differs from, or is different from the previous adiabatic proofs, in the sense that our Hamiltonians should prepare both program register and work register, not just like the previous ones that were working on work registers only. And there are still a lot of more interesting questions to ask, and we are just working on a hybrid architecture. Consider a system that the Hamiltonian is pretty much the same, but we are trying to replace the control X alpha with real measurements, and although it seems incompatible to keep it in the ground state, we are trying to use effects like the Zeno effect to force the system to remain in the ground state. And we will claim that this is a type of measurement-based computation, but it obtains its robustness from the adiabatic quantum computation and parallelism from the measurement-based quantum computation. Thank you for listening.
Any questions?
The Hamiltonians which occur in your construction, are they, how many bodies or parties are they acting on simultaneously? Are they two-body Hamiltonians or are they
Right. In our configuration, it's three-body Hamiltonian, but if you don't have any problem to increase the dimension of the Hilbert space dimension of the program register, you can make it a two-local Hamiltonian, but the qubits dimension will increase.
How much does it increase by?
It will yes. No, if you add the locality, more locality, it will become a 14 degree. So it's now 12.
But then you have a two local.
Yes, then you'll have a two local Hamiltonian.
Are there any other questions?